had by dx. So what is that false that error which you mentioned here?
Please repeat. What did you say?
Sir, we cancelled two terms yesterday. A du had by dx and
Yes.
x equal to L by 2.
Yes.
So what error it is called?
Oh, that's all. It is also discretization error. Because this error, as I asked you to explore, if you improve the interpolation model to cubic interpolation, right? So use 4 noded elements, and then you will find that you will not have this error. I mean the du by dx that you compute from different elements, they will at the common node, they will be exactly equal, because your interpolation model coincides with the true solution of the problem. True solution is cubic polynomial, and if you interpolate using cubic polynomial, you will get the exact result. And everything will be satisfied according to whatever the way it should be in the classical solution. Right? So the only thing that is happening here is, because of this weak form, your degree of continuity requirement is reduced. So your approximation is not really as smooth as directed by the governing differential equation of the problem. But still, using that lower degree approximation, which does not satisfy the governing differential equation, you are still able to get a very good approximate solution. You are able to decipher the trend, you are able to decipher the design quantities reasonably well, and you can also derive this, what you say that it is an error. It is indeed an error, discretization error, but that discretization error, that gives us extent of that discretization error gives us very useful information about the degree of approximation or the quality of approximation. Right, so let me go through that fine point once again. I intended to do that anyway because yesterday we forgot to record the session. So let's run through those two. We dealt with this element level equilibrium equation. This is the result of weighted residual statement. So this weighted residual statement, which weighted residual statement over the whole domain is approximated as the sum of weighted residual statements over non-overlapping two subdomains. So this is subdomain 1, element 1, and this is subdomain 2, element number 2. Right? So the total weighted residual statement over the total domain omega is given as sum of contributions of weighted residuals from two non-overlapping domains, omega 1 and omega 2. And we go through this weighted residual procedure over the individual elements using interpolation functions of individual nodes which define these elements. So element 1 is defined by nodes 1 and 2. So the interpolation functions corresponding to nodes 1 and 2 in element 1, they will be used as weighting functions, and we go through the same process, standard process of weighted weak form and weighted residual statement, and eventually we end up with an algebraic equation in terms of the primary variables, values of the unknown values of the primary variable at the nodes, so u1 and u2. And for two unknowns we have two weighting functions, that two interpolation functions, and we get two equations for element 1. And similarly, when we use element number 2, the interpolation functions for element number 2, they will be used as weighting functions for the domain of element 2 ranging from L by 2 to L. And again we go carry on with the process for weighted residual statement and end up with the two algebraic equations in terms of the primary variables of element number 2, that is displacement at node 2 and node 3. So the next step that is left is what we need to do here. So summation, this element level 1 equilibrium equation represents this weighted residual statement term, and element number 2 equilibrium equations represent this part of this weighted residual statement. Now we need to take care of this combination part. How do we combine these two sets of equations, simultaneous equations, linear simultaneous equations? So that is done by the process of assembly. It can be easily arranged in automatic mode by using the simple algorithm, but visually for this small problem where we have a very few number of degrees of freedom, we can actually carry out this assembly in a visual way. We just list out the degrees of freedom to which individual terms correspond to. So there are 3 degrees of freedom total in this problem, in this finite element mesh. So U1, U2, U3, 3 degrees of freedom, 3 primary variables at 3 nodes, and these are the columns and these are the rows designated by that. And we plug in the terms from the two equations. So for example, element number 1 would correspond to, would occupy positions corresponding to U1 and U2 and F1 and F2. Similarly, element number 2 would occupy positions corresponding to U2 and U3 and F2 and F3. Node 2 and 3 belong to element 2 and node 1 and 2 belong to element 1. So node 2 is common. So node 2 will receive contributions from both the elements. And when we assemble, when we put these entries from element level equations into this global equation comprising all the degrees of freedom of the entire domain, we get this simple standard format, Ku is equal to F. So this is F1 and this is F2 from element number 1 and this is F2 from element number 2, as you can see, and this is F3 from element number 2, and this is of course F1 from element number 1. So after we substitute this, we see that there is this term AE times du by dx at x is equal to L by 2 minus AE times du by dx at x is equal to L by 2. Right? So this is like expressing the equilibrium of these forces of at any section when a body is looked at a particular section, two separate parts, free body diagram, and the free body diagram would involve a pair of equal and opposite forces at the points of point of section. So it is these plus and minus forces, they are similar to what you observe from what you should get from a free body diagram. But the little complication here, this is fine as far as mechanics goes. You all are familiar with this free body diagram concept and action reaction pair. But a little complication here is that this term is contributed by element number 1. So du by dx that you are computing is actually based on the approximation of u over element 1. And this term is contributed by element number 2. And du by dx that is being computed is coming from the approximation for u over element number 2. So u is approximated as a linear interpolation between u1 and u2 in element 1, and in element 2 it is constructed as a linear interpolation between u2 and u3. So these two are going to be independent, and in general they will not exactly balance each other out. But for analysis purposes, during the process of assembly, we do take care of this internal equilibrium, and we impose this condition of equilibrium here and generate the force vector accordingly. And once we have this force vector, we impose this natural boundary condition at x is equal to L. So AE times du by dx at x is equal to L is given as point load Q. And once we have this natural boundary condition imposed, the force vector is ready. Equivalent nodal forces is completely defined. Then we go on to impose the essential boundary condition of the problem, that is u at x is equal to 0 is equal to u star, some prescribed value. And that is done by using stiff spring approach. We add a very high stiffness to the degree of freedom corresponding to u1, and we make suitable provisions in the force vector corresponding to degree of freedom u1 such that we end up with a situation alpha times u1 is equal to alpha times u star. And during the process of solution, it will evaluate to u1 will be evaluated to u star, the prescribed value. So once the essential boundary conditions are prescribed or imposed, then this system of equations linear system of equations can be solved. So Ku is equal to F, and we can solve for this system of equations. So K, after imposing this essential boundary condition using this penalty function approach or stiff spring approach, so this stiffness matrix will now look like 1 plus alpha minus 1 0 minus 1 2 minus 1 0 minus 1 1, and common factor is 2AE by L. And this system of equations can be solved, and we can get the solution. We can get the solution as u2 and u3. u1 is of course 0. u2 can be evaluated as L over 4AE multiplied by 7Q naught L by 12 plus 2Q. u3 can be evaluated as L over 4AE multiplied by twice Q naught L by 3 plus 4Q. And that's more or less the problem is solved. Now you have the three displacements of the model, that is u1, u2 and u3 are known. See, there were three unknowns. The entire domain was divided by this mesh was defined by these three nodes, and at the end of the solution you have been able to compute displacement at u1, that is of course prescribed as essential boundary condition, and you know what is the solution, what is the displacement at this node 2, and you know what is the displacement at node 3, u3. Knowing these three displacements, we can find out what is the displacement varying in between within the interior of each of these elements. So displacement variation within element 1 will be given by interpolation between u1 and u2. So u1 n1 plus u2 n2, that will be the variation of displacement within element 1. Similarly for element 2, it will be u2 n2 and plus u2 n3 or ni and j if you wish to call it that way in local numbering. So we go back and substitute these models. So element number 1, displacement approximation in element number 1 are given as interpolation between these two nodal values, u1 and u1 is 0 and u2 is equal to this value. So you get this linear variation in u, and AE times derivative of that du by dx, that is the axial thrust within the element 1, and you take the derivative AE times du by dx, and this is what you get axial thrust in element 1. And similarly, going to the element number 2, we have u2 multiplied by interpolation function for node 2 in element 2 plus u3, the displacement for at node 3, multiplied by interpolation function for node 3 in element 2, and combine the terms and you again get a first degree polynomial linear function in x, and you take the derivative to compute the axial thrust. So AE times du by dx, and you get this constant value. Simplifying term, I mean, this is what you get. So these are the two axial thrusts, and the difference between these two is what we, I mean, they should actually be at L by 2, they should be equal, but of course this is a constant value over the entire element. So this is some kind of average thrust value over which is valid over the entire element length, and this is also the average thrust over the entire length, right? And we can now look at the variation. So this blue curve, that is the cubic polynomial, that is original displacement which we computed using analytical solution of the differential equation for this linearly varying surface traction, skin friction, and point load, applied point load. And this green line is the one element approximation, linear element, two noded linear element representing the entire domain. So this is the displacement which was predicted by the one element approximation. Now if we use H refinement, that is refine the finite element mesh by dividing the domain into two elements instead of one, again sticking to linear models. So two linear elements, we divide the domain and we get this cyan colored variation. So straight line between one straight line between 0 to 0.5 and another straight line between 0.5 to 1. So as you can see, the improvement in result is actually very, very significant just by having the length of the element. The capture in the trend is very good in the displacements. And for the stress resultants, the axial thrust for one element, this is the average axial thrust over the entire domain. So as you can see, this is the quadratic axial thrust that was computed using analytical solution, and the average value of this is what you compute from one element approximation. And if we use two element approximation, then average value of thrust is predicted over individual elements. Right, so this is thrust for element 1 and this is the thrust for element number 2. Now what is important to note here is near midpoint of this element, the value of this secondary variable or this stress field or the stress resultant is very close to the true value, right? In actual finite element analysis, we will never have this true result. So what we can do is pick up this value, 1 point here, 1 point here, and we also know what is the value of in this problem. We also had this natural boundary condition specified at x is equal to L. So at that point also we have satisfied the boundary condition. So we also know what is the thrust value at that point. So using these 3 points, we can actually construct a quadratic function which will be very close to the true variation of the axial thrust that you have, that the problem should have. And we can use this approximation to the true solution, and the difference of that approximation to true solution from the computed solution for these stress resultants, and that gives us a measure of error in the finite element analysis. And that error or error density, if I divide it by per unit length or volume of the element, so that gives me the error density, some kind of number. I just need to define a number just to judge the size, and that can be used for refining the mesh. So where I need to refine, for example, in this case, the deviations are much larger for in element 1 compared to element number 2. The deviation in element number 2 range from only 1 to maybe 1.17, right? So this is not too much of a deviation, whereas for element number 1 it ranges from 1.17 to 1.5. So this is actually very large variation here. So it is more prudent if we can do 2 things here. Either instead of taking 2 elements of equal sizes that we took as 0.5 and 0.5, I can reduce this to maybe 1/3, 0.6 or 0.3, and take this element as 70% of the length, second element. So that is called H refinement. I mean the error density would be more or less would be controlled. So extent of error in this element would be reduced, because if the element size is reduced, then the average error, average thrust predicted would be somewhere here, right? And that would reduce the extent of error, and at the cost of increasing error here. Slightly it will increase the error here, but if all of those errors are within the acceptable tolerance, then all is well. Otherwise we will need to increase the degree of interpolation as well, or add more number of elements. Nothing stops us from adding more number of elements or even increasing the number of increasing the degree of interpolation, but all of that will increase the problem size. Number of variables to be solved for will increase. So in essence, this is the crux of what we do in adaptive finite element analysis. We, using the results of a typical finite element run, we conduct this kind of posteriori error analysis, and then take a call on whether the results of finite element analysis are acceptable or whether a refined finite element analysis is required. And according to that, the mesh is refined again if required, and then the analysis is repeated, and again followed by similar posteriori analysis. So, Pratmesh, did I answer your question? Okay, good. So any questions so far?
So,
Yeah.
so then accounted the boundary is very good. I mean, integration of R omega W into D, sorry, R gamma into D gamma.
Yes.
Vector. So then we have considered then at the boundary points we have only lie difference. We have solution at the
Where we impose the natural boundary condition, there is no error. I mean, there is of course, because it is average, so it will be an error. So the natural boundary conditions are always satisfied in approximate sense.
So that in this graph, the 2 points are not to the
Pardon?
at point, so in the graph, sir.
Yes. Yes.
The 2 points of Z solution and a primitive solution at boundaries, so not correlated.
Yes, they are not correlated.
So then what would happen, sir, if we don't account for that
Nothing happens. I mean, it is an approximate solution, and if you are not happy with this quality of this approximation, you can further refine the mesh and you can repeat the analysis. It will keep on improving. See, what will happen is, if you refine the mesh, let's say if I divide this into, instead of 2 elements, I use 4 elements of again equal size, then I will have one element, first element would be of this length, and then the stress resultant would be somewhere around this. For second element, the stress resultant would be somewhere around this. What is it? Let me, just a minute, let me. So, element number 1 would be about 0.25. 0.25 would be somewhere here. Fine. So for element number 1, I will have stress would be somewhere here. For element number 2, it would be somewhere here. For element number 3, I will have stress resultant would be somewhere here. And for element number 4, I will have stress resultant would be, what is that? 0.7, average value would be somewhere here. Somewhere here. So as you keep on refining, you will find that the stress resultant, the difference between the stress resultants at inter-element boundaries, that will keep on decreasing, and similarly the error between this specified value and the value that is predicted will also keep on decreasing.
But initially we improved the boundary condition, we taken into account, we taken care of boundary conditions, so I thought that it should be improved, it should, as
So we did not,
should be.
we imposed, yes. We imposed the boundary condition on du by dx, right? So let me just say, so this is the approximation, that is AE times du by dx over element number 1, and this is the approximation AE du by dx at for element number 2. Now obviously you had element 1 is a first degree polynomial, right? So it will be a0 plus a1x. So du by dx of course is going to be constant, a0. So ae times du by dx, so that's what you get here, constant. So now obviously your true solution is quadratic. You cannot, if you have to approximate a quadratic variation with a constant, you will only be able to get whatever is the best fit solution in the case, least square sense. And that is the best you can do. That is the nature of approximation. And similarly here, you are imposing the boundary condition, at x is equal to L, AE, you impose the boundary condition here as AE times du by dx at x is equal to L as Q, right? So that is what you specified here, and that is going into calculation of U1 and U2 and U3. So these values were calculated accordingly after you impose this boundary condition, but this boundary condition was imposed on this linear variation field of displacement, right? U2 is again let's say it's b0 plus b1x. So du by dx is again just b0. So what you have done is essentially restrained this value of b0, that's all. Right, this b0 was computed, this effect of this imposition of boundary condition q has influenced the computation of this coefficient of polynomial approximation b0. If you change this value here, q something else, your value of b0 will change, but it will still have to be constrained by the laws of polynomial. There is no way you can approximate a second degree polynomial by a constant term. That can only be in the best fit fashion. Right? So natural boundary conditions will always be satisfied in approximate sense as long as they remain, those are the secondary variables. We are not directly approximating those secondary variables. These agreement will in general improve with the refinement. As you refine the finite element mesh, you will begin to see the improvement in agreement. So right now your error is of the order of what? This is 1, this is 1.05. So it's not even 5%. Right? So this error that you are having, that you are saying, it is actually less than 5%. Instead of 1, you are getting 1.05 approximately. So, I won't call it a very large error by any stretch of imagination. In one element approximation, the error was of the order of 15%. Right, so this one is approximately 15%. So you changed from, you were able to reduce this error of 15% to 5% in two element approximation. It will further reduce if you go for further refinement, and gradually it will keep on improving, but it will never be exactly equal to 0. First rule, 0 cannot be computed, so but unless you choose approximation for u hat exactly same as the approximation that is consistent with the true solution, unless you choose that, there is no way this error will ever be able to vanish completely. So, does that make sense? Or you are still not convinced?
So, can we say that by imposition only the imposition of boundary condition minimizes the error at the boundary points? Can we see that? It minimizes.
It minimizes the error in the least square sense, and not just at the boundary points. We are concerned about the solution. We are concerned about the solution of the primary variable. Secondary variable are just the byproducts of the solution. Our primary approximation, we are approximating u, we are not approximating axial thrust T. Axial thrust is a byproduct of this approximation. And our approximation is definitely improving. If you look at the displacement, I mean, from this we come to this, and that is of course significant improvement. And I told you about this error that we have is not a restraining condition. We can derive very close variation, very close approximation to this true solution by using this interpolation of the stress field, as I discussed in this posterior error analysis, and that is a reasonably, very good estimate of the stress resultants, and we can use that for analysis or for design purposes if required. So we have found the finite element analysis. We can use this value at the midpoint. We can use this value at the midpoint of the element, and we can use this value at the end point, that is the boundary condition. So at these points we have 3 points for thrust, AE times du by dx, and we can construct a second degree polynomial through these 3 points. So eventually we should be able to get something like this. It's fun playing with colors in this mode. Right, so instead of this solid line, you might be able to get this approximate line. Fair enough? Close enough solution for the axial thrust variation of the problem, and that should practically serve all the needs for error analysis in finite element refinement, and also for estimating the design quantities, the axial thrust variation in the element. This is important because if you take a decision only on the basis of this value and take it as a gospel truth, obviously you are going to underestimate what is the stress level in this part of the domain. And if you ignore this and just based on this you put it just at the limiting value of the failure point at based on this result, then obviously your system is going to perform very very badly. Right? You need to understand that this is the average value. Yes, please.
So I want to ask something that we did all the calculations for domain residual part for this term.
Yes.
In weighted residual statement, we have two terms, domain residual and boundary residual. And we did all the calculations for domain residual.
Yes.
So I'm concerned about the boundary residual.
So there is no boundary residual. We impose the boundary conditions on this boundary term that come from the weighted residual statement weak form. See, in this problem there are two boundaries. This value was prescribed at x is equal to L here, and displacement was prescribed at this point. Right? So we impose this displacement value at u is equal to 0. So this value was prescribed at this point, and that has been imposed prior to computing the solution, and this boundary condition was prescribed at this point, and that has also been imposed in the first term. The boundary term that was appearing in the first term, we had this AE times du by dx at x is equal to L in the boundary term. So this has been substituted, whatever was the boundary condition specified, and that was arranged there, right? And subsequently the solution was computed. So the boundary residual as such does not appear in the statement of weighted residual in finite element formulation. The boundary conditions are accounted for during the process of assembly of individual element contributions of weighted residual, domain residual statements. The boundary terms associated with domain residual statements, the natural boundary conditions and essential boundary conditions would be imposed on those. That is what we did here. So we assembled this system of equations from two equations, two elements. So this term, this is of course the unknown term, and we don't need to do that because essential boundary condition U1 is prescribed, and this is essentially the reaction of the support. So we don't need to know this value. That will be computed as an after solution, and that is computed as axial thrust. At the other end, we have this term, and we simply replace. du AE times du by dx at x is equal to L is given as q. So we substitute it here, replace this by q, and that is the imposition of natural boundary condition. So there is no residual as such. Boundary residual. Right, so any other question? Yes?
This is how the ATM calculations are done in the ATM software also, like they are taking the decimal statement and the simulation they are performing that.
All this is already built into that. So for finite element solution, what you do is essentially you start finite element solution from, let me say, this is already known. When you choose the element and you define the geometry, then as you can see that these are defined by the coordinates of these nodes. So the moment you define the nodes and their coordinates and the element definition in terms of these nodes, these quantities are automatically defined because they are programmed in such a way that they will pick up these coordinate data and populate these values automatically. And then for these integrals are already known. The only thing that is, if you see, this is constant, so this there is nothing that changes here. So the only thing that you need to do here is, if the forcing function that changes, so which will be, in this case I intentionally chose this linearly varying skin friction, so then this term needs to be evaluated. So this term will have to be evaluated, and that is integrated depending on different element and different variation of skin friction or forcing function term, and you get what is what we call as nodal equivalent values of the forces, equivalent nodal values of force. So distributed force is transformed into equivalent nodal values, and the idea is the distribution is such that the work done by the nodal equivalent values of forces in moving through these nodal values of the displacements that we have at the nodes is same as the work done by the distributed force in moving through continuous displacement field. Right? So that is work equivalence. So you impose the condition that the amount of work done should be same, and then you define the equivalent nodal values of forces, and once you have that, then it's just this algebraic equation, and every element will result into this kind of algebraic equations, set of algebraic equations for each element. So what is done in finite element software is generate these kind of element level equations for one element, then assemble it into the placeholder over global assembly. So just as we did for element number 1, we populated the terms corresponding to degrees of freedom 1 and 2. And then we moved to element number 2, populated the terms corresponding to degrees of freedom from element number 2, and so on. And after the complete assembly, we look at these terms and impose the boundary conditions wherever those are specified. And these terms, this is in the interior of the domain, so we don't even bother about it, because by this logic, by the mechanics, basic mechanics, they should be cancelling out each other, so we don't even bother to compute this at the interior of the domain. We only bother about the secondary variables when this boundary of the element boundary coincides with the domain boundary. So we don't even bother about these secondary variables in the interior nodes. So node 2 here is in the interior of the domain, and that we know that they will cancel out, or they should ideally cancel out each other. So we don't even bother about accumulating those. We just account for these boundary terms, secondary variable, only when boundary condition is specified on them and the element boundary coincides with the domain boundary. So in this case, node 3 is the boundary of element number 2, and it is also the boundary endpoint of the original problem domain. And once we do that and impose this boundary condition, the equation is solved, and rest of the things are what we call as post-processing phase. Substitute it back into the equation and go back to element level definitions for calculating the displacement variation within the element, and then calculating the secondary variables. So these are all what we call as post-processing. And the preparation of element data that we had earlier, So this is what we call as pre-processing. And everything that follows here is what we call as basic finite element analysis. This is finite element analysis. So generally pre-processing and post-processing, although we did it here manually, and that was the way it was done in the initial days of finite element analysis, but now it is often delegated to very powerful graphical user interfaces. Complex geometries can be generated by using modeling tools, and finite element mesh, appropriate finite element mesh can be generated automatically, and the entire nodal connectivity data can be generated automatically by those pre-processing tools. And similarly, post-processing also, this numerical data is difficult to make sense of, and as you can see that that simple graphical representation is so much appealing. It conveys so much more than just discrete numbers, that if I tabulated the values, these are the displacements of node 1, node 2 and node 3, it is not so much appealing in comparison with when you see the complete variation over the visual comparison of what is the true solution and how the finite element approximation. Again, I need to emphasize this point. True solution is a cubic polynomial. Finite element approximation is just a linear variation. But even a linear variation is able to approximate that cubic variation very closely in the two-element approximation. And the approximation will further improve if you define the finite element mesh. And similarly, the secondary variable, the approximation, is little inferior, one order lower than the approximation for the displacements, but still you can get a very good idea about the stress fields if you sample the stress values at near the midpoint of the element, or also we have something called Barlow stress points. We will talk about it in the later part of this course. So we sample the stress at Barlow stress points and in different elements, and then generate an interpolation model for stress field, and that interpolated stress field is going to be very close to the true stress field, and that can be used for performing posteriori error analysis in the finite element solution and take a call on whether we need to improve the finite element mesh or not. So did I answer your question, Rituraj?
Yes.
Okay.
Thank you.
Okay, so we stop here. Okay, yeah, yes, Ishan.
So in case of approximation of 1 degree for cubic polynomial, we can also have the quadratic as a function as approximation,
Of course, you can.
or cubic.
Yes, yes. But the only problem is your problem size will also increase. For quadratic, you need 3 nodes in an element.
We have 3 nodes.
For cubic, you will need 4 nodes in an element. So that means your number of degrees of freedom are going to increase, your problem size is going to increase.
Yes, sir.
So that is the only offside. And it is, even for this small problem, you will find that it becomes very soon, it becomes very difficult to handle manually. If you use quadratic element, you will find that it is almost I mean, without computer tools for solution of simultaneous equations, you cannot handle that. So finite element method in general cannot be implemented without assistance from computers, but even computers have their limitations. They are finite machines, so their capacity is limited. So it is often a very delicate balance is required between desired accuracy and what is practically feasible based on the kind of computer system you have at your disposal. Okay. So we stop here. Thank you.
Thank you, sir.